We're now changing the subject matter considerably. Until now, I've been talking about simple models such as finite automata or context-free grammars that let us model mechanisms like communication protocols or processes like the parsing of programming languages. Today we begin to study the other side of automata theory, the part that lets us show certain tasks are impossible, or in some cases possible but intractable. That is, they can be solved, but only by very slow algorithms. It might not be obvious, but just because we can state a problem doesn't mean there is any algorithm at all that can solve it. For example, can you devise an algorithm to tell whether the complement of a context-free language is empty? That is, does a grammar generate all strings over its terminal alphabet? It turns out you can't. And we're going to learn the theory that lets us prove facts of this kind. We begin with a central theme of the study of what can be solved by computer algorithms. The idea that all data can be represented by integers. The idea of countable sets, those whose members can be assigned integers 1, 2, 3, and so on, is essential here. We're going to meet the Turing machine, which is in some sense the ultimate automaton. It is a formal computing model that can compute anything we can do with a computer or with any other realistic model that we might think of as computing. Turing machines define the class of recursively enumerable languages, which is thus the largest class of languages about which we can compute anything. There's another smaller class called the recursive languages that can be thought of as modeling algorithms, computer programs that answer a particular question and then finish. I realize the concepts are vague at this point, but we'll get to it all in good time. If you took a modern course on programming, you are undoubtedly introduced to the importance of data types or classes. But when you look under the hood, how these types are represented inside the computer, you see that there is only one type, strings of bits. We could base our whole theory on strings of bits, but it is more convenient to convert binary strings to integers. We can almost see how to do that, since integers can be represented in binary notation, but there's a small glitch we'll get to. And to make the idea that all the world is integers even more pervasive, remember that the programs that computers execute are also, under the hood, just strings of zeros and ones, and therefore can be regarded as integers. That lets us talk about the 100th program and things like that. As we shall see, the fact that programs and data are at heart the same thing is what lets us build a powerful theory about what is not computable. As a simple example of a type that is really integers, let's look at character strings. Strings of ASCII characters can be thought of as binary strings, 8 bits to a character. Or if you use Unicode, you need 16 bits per character, but the idea is the same. Strings in any alphabet can be represented by binary strings. And binary strings are really integers. Thus, it makes sense to talk about the ith string for any I. However, we have to be careful how we do the conversion from binary strings to integers. Because binary strings can have leading zeros, there is not a unique representation of an integer as a binary string. More to the point, if you do the obvious conversion, then strings like the ones shown all seem to be the integers 5. But we can't call 2 or more different strings by the same integer. However, there is a correspondence between binary strings and integers that is 1-to-1 and almost as simple. Put a 1 in front of any binary string and then treat it as an integer. This way, no two strings can correspond to the same integer. For example, if we're given string 101, then put a 1 in front of it and treat 1101 as a binary integer, and you'll get 13, by the way. If you put a 1 in front of 0101, then this integer is 21, and so on. For a wilder example, consider images as a data type. There are many representations of images. Let's talk about GIF. A GIF file is an ASCII string, so convert ASCII to binary, and then the binary string to an integer in the way we just discussed. And bingo, you have a notion of the ith image. Here's another wild example, proofs. A proof can be viewed as a sequence of expressions or assertions in mathematical form, each of which is either given or follows from previous statements in the sequence by certain logical rules. We can encode mathematical expressions in Unicode. It has pretty much any symbol you would use in mathematics. But we can convert any expression to a binary string and thus to an integer. There is again a small glitch. A proof is a sequence of expressions, not a single expression, so we need to fix on a way to separate a sequence of expressions. We also need to indicate whether an expression is given or follows from previous expressions. We thus need to introduce two new symbols into our strings. One is a comma to separate expressions. We can't just use the Unicode comma because the expressions themselves may use this symbol. The other is a marker that says, this is a given expression. The following technique is useful not only here, but in general as a way to introduce new symbols with any meaning into binary strings while still keeping the strings binary. First, given a binary string, expand it by inserting a 0 in front of every bit of the string. For example, 101 becomes 01, that's the first one, 00, that's the 0 in the middle, and then 01. Now, as a consequence of this change, strings have no consecutive ones. Use strings of 2 or more ones as the new symbols. For example, we'll use 111 to mark a given expression and 11 as the marker for the end of an expression. Here's an example of what a proof as a binary string could look like. The initial 111 can only mean that the expression to follow is a given expression. Here is the expression itself. It was originally 101, but we expanded it with a 0 in front of each symbol. Of course, 101 is too short to really be an expression, since even one Unicode character takes 16 bits, but let's not worry about that. This 11 marks the end of the first expression. Notice that this 1 cannot be part of a special marker, since all expressions without the special markers have even length, and this 1 is the 6th symbol in the expression. Here's another given marker. And another expression. This one was 0011 with zeros embedded. And another expression ender, and so on. As we said, programs in a language like C or Java are also a data type and can be represented by integers as if they were data. First, represent the program as an ASCII string or in some other alphabet like Unicode if the language requires it. Then convert the character string to a binary string and then to an integer. Now we can talk about the ith program. And this should worry you. There really aren't more programs than there are integers. While that number is infinite, you may be aware that there are different orders of infinity, and the integers are the smallest one. For example, there are more real numbers than there are integers, so there are more real numbers than there are programs. That immediately tells you that some real numbers cannot be computed by programs. We'll get to more concrete explanation of what the dearth of programs really means shortly. We have an intuitive notion of when a set is finite or infinite. A set is finite if there is a particular integer that is the count of the number of members of the set. The term for the count of the number of members is cardinality. For example, the set containing A, B, and C is a finite set, and its cardinality is 3. The formal definition of a finite set is one for which it is impossible to find a one-to-one correspondence between the members of the set and a proper subset of that set. Well, actually, the formal definition of an infinite set is one for which there is a one-to-one correspondence between its members and a proper subset. Then the finite sets are formally the sets that are not infinite. For an example, the positive integers are an infinite set. We can let the proper subset be the even integers, and the one-to-one correspondence matches 1 with 2, 2 with 4, 3 with 6, and so on. Every positive integer I is matched with a unique even integer 2i. A countable set has a one-to-one correspondence with the positive integers. For example, the set of all integers, positive or negative, is countable. A correspondence maps 0 to 1, minus I to plus 2I for all I equal to or greater than 1, and plus I to 2I plus 1 for all I equal to or greater than 1. As a consequence, the positive and negative integers get interleaved in the ordering as 0, minus 1, 1, minus 2, 2, and so on. The binary strings are also countable. We saw how to assign a unique positive integer to each binary string by putting a 1 in front and treating the result as a binary integer. Likewise, the Java programs can be put in one-to-one correspondence with binary strings and then with integers. Many of these integers represent flawed Java programs, things that don't compile, but that is not important. The important thing is that every working Java program has a unique integer. A rather surprising point is that pairs of integers can be put in one-to-one correspondence with the integers themselves. A simple way to see this is to explain an ordering of the pairs as first pair, second pair, and so on. The ordering we want is first by sum, and then for pairs with the same sum by first component. Thus, 1, 1 comes first. It is the only pair with a sum of 2. There are 2 pairs with a sum of 3, these guys, and we put 2, 1 ahead of 1, 2 because it has the higher first component. Then come 3 pairs with sum 4, these 3, again ordered by the first component. You can, in fact, figure out a function f of ij such that the pair ij is the f of ijth in that order. But the important point is that some such function exists, and therefore it makes sense to talk about the ith pair of integers. We call the one-to-one correspondence between a countable set and the positive integers an enumeration of the set. Thus, strings, programs, proofs, and pairs of integers, for example, have enumerations. Now, let's look at the set of all languages over some fixed alphabet, say 0, 1. Could this set be countable? The answer is no, and we can prove it. Suppose it were possible to enumerate the languages so every language over 0, 1 was the ith language for some I. We already know how to enumerate binary strings, so we can talk about the ith binary string. Now, I'm going to define a language L. L is the language containing those binary strings W, such that W is the ith binary string. That must be true for some I. And W is not in the ith language. L is surely a language over alphabet 0, 1. Since we're assuming that the languages over 0, 1 are enumerable, that means that for some j, L is the jth language. So let x be the jth string. Surely some string is the jth in the enumeration of binary strings. Now we can ask, is x in L? It turns out that if it is, then it isn't, and vice versa. To see why, remember the definition of L. L contains W if and only if W is not in the language that corresponds to the same integer I that W corresponds to as a string. So let's focus on the case where W is x, the jth string. In that case, the value of I is j because we know x is the jth string. Further, we know that L is the jth language, so both L, the language being defined, and the, quote, ith language mentioned in the definition of L are all the same, and they are LJ. Thus, when we read the definition of L as it applies to x, it says that x is in L, which is L sub j, if and only if x is not in L, again, which is L sub j. We have a contradiction. X is neither in L nor not in L. That's an impossible situation, and we conclude that our assumptions are wrong. The only unproved assumption we made was that we could enumerate the languages over 0, 1, so that is false. We can't enumerate such languages. As a result, we see that there are more languages than programs, since the programs can be enumerated. A particularly bad consequence of this fact is that there are languages for which no program can tell whether or not a given string is in the language. On the bright side, none of these strange languages are context-free, or therefore not regular. Uh, since the CYK algorithm gives us a membership testing program for any context-free language. The process of coming up with the language L that can't be in any enumeration is called diagonalization. The reason should be apparent from this picture. Imagine an infinite matrix in which the rows correspond to languages and the columns to binary strings. A 1 in the entry for row I in column J means that the jth string is in the ith language. 0 means it is not. If we could enumerate languages, then we could create such a table. Look at the entries along the diagonal and complement each one. That is, replace 0 by 1 and vice versa. Here's what it looks like. The complemented diagonal, rotated 45 degrees, looks like a language. It tells which strings are its members. Here, strings 1 and 2 are not in the language, the third and fourth are, and so on. But this language cannot be any row because it disagrees with each row in at least one position. In particular, it disagrees with the ith row in the ith position. We're now ready to look at the theory of Turing machines. One important purpose of this theory is to prove certain particular languages to have no membership algorithm. The first step is to prove certain languages about Turing machines themselves not to have membership algorithms. We're then going to introduce the important notion of a reduction from one problem to another. These are proofs of the form: if there is an algorithm for problem P, then there is an algorithm for problem Q. We'll draw this as Q is reduced to P. If we already know that there's no algorithm for Q, then how could there be an algorithm for P? Because if there were an algorithm for P, then this reduction would give us an algorithm for Q. Okay. By use of reductions, we don't have to resort to diagonalization or another trick to prove that P has no algorithm. Here is the picture of a Turing machine we should keep in mind. There is a state which, like all other automata, can only be in one of a finite number of states. There is a tape, this, infinite in both directions and partitioned into squares, each of which can hold a symbol of a finite tape alphabet. There is a tape head that always points to one of the tape squares. The Turing machine makes moves just like the finite automaton or pushdown automaton. For the Turing machine, the move is determined by the state and by the tape symbol under the tape head. In one move, the Turing machine can change its state, write a new tape symbol over the old one in the square its head is scanning, and move the head one square left or right. We might ask why we introduced the Turing machine rather than representing computation by C programs. While you could develop a theory around programs without using Turing machines, it would be much harder. The thing that we'll come to appreciate about Turing machines is that they are so simple in their operation compared to programs in a programming language or even real computers. That wouldn't matter if Turing machines could not mimic real computers, but they can, as we shall argue. And in fact, one could argue that because Turing machines have infinite storage capacity on their tape, they are even more powerful than computers, since computers always have a finite amount of storage, however large that may be. But the difference is not essential, since in principle, we could always buy more storage for a computer. One could counter-argue that the universe is finite, so where are you going to get the atoms from which to build all those disks? But even if you accept that the universe is finite, the limitation doesn't seem to be affecting what we can compute in practice, so we're never going to argue that a computer is weaker than a Turing machine in a meaningful way. So here's the formalism we'll use for Turing machines. There's a finite set of states, and we'll follow our tradition of using Q for this set. There's a finite input alphabet for which we use the traditional sigma. There's a finite tape alphabet, gamma, which always includes the input alphabet. The transition function is, as always, delta, and we'll talk about how that works next. There's a start state Q0, a member of the set of states Q. Again, this is as before. There's a blank symbol, which we usually represent by capital B. This symbol is in the tape alphabet, but is never an input symbol. And there's a set of final states, F as usual. And there are several conventions about letters we shall use. They are consistent with our earlier conventions for finite and pushdown automata. Lowercase letters at the beginning of the alphabet are still symbols of the input alphabet. Now, capital letters at the end of the alphabet are tape symbols, which might or might not be input symbols. Lowercase letters at the end of the alphabet are strings of input symbols. Again, that's as usual. And Greek letters at the beginning of the alphabet are strings of tape symbols, which again may include some input symbols. Now, let's see the transition function delta for a Turing machine. The Turing machine is deterministic, and moreover, it does not have to have a move in any situation. Delta takes two arguments, the state and the symbol scanned by the tape head. Delta of QZ, for state Q and tape symbol Z, can be undefined, in which case the Turing machine can make no more moves scanning a Z in state Q, and the Turing machine is said to halt. But if delta of Q and Z is defined, then it is a triple PYD, where P is the new state, Y is the symbol that replaces Z in the square being scanned on the tape head, and D is the direction for the tape head to move. This direction is either L for left or R for right, and the move is by one square. Here's an example of a Turing machine. Its input symbols are 0 and 1. The Turing machine scans right on its input looking for a 1. If it finds a 1, it changes it to 0 and goes to a final state F and halts. However, if it sees the blank symbol before seeing a 1, it changes the blank to 1 and moves one square left, repeating the process just described. There are two states for our Turing machine, Q and F. Q is the start state and F is the final state. As we mentioned, the input alphabet is 0, 1. The tape symbols are only 0, 1 and the blank B. One move of the Turing machine is given here. It says that in state Q, scanning a 0, in state Q scanning 0, it stays in state Q, leaves the 0 on the square it was scanning, and it moves right. Another rule says that if it is in state Q and sees a 1, it goes to final state F, replaces the 1 by a 0, and moves right. It doesn't matter which way the head moves in this situation since it has accepted its input, but it always has to move left or right, so we'll say right. The last move of the Turing machine is this. It says that in state Q, while scanning a blank, it replaces the blank by 1 and moves left, staying in state Q. Here's the beginning of a moving picture of this Turing machine. The three moves are shown in the upper right, with the move that is applicable in a given situation shown in red. Here, the Turing machine has just started. It is in its start state, and the tape head is at the left end of the input, which is 0, 0 in this case. That is, here's the input. The rule in red says that in state Q, scanning 0, it moves right and leaves the state and symbol unchanged. So we'll see that on the next slide. Here it's done that, and it is in the same situation, again scanning a 0, so it again moves right. Now it sees a blank on its tape, so another rule is applicable. This rule says that stay in state Q and replace the blank by 1 and move left. So it's made those changes, and the first rule is applicable again. The Turing machine is going to move right while leaving the state and symbol unchanged. Here the second rule applies. In state Q, it is scanning a 1, so it goes to the final state F, replaces the 1 by 0, and moves right. Here we see the effect of the last move. The Turing machine has no move for when it is in state F scanning a blank, so it halts. It has also accepted, since F is a final state. Moving pictures of a Turing machine can get a bit cumbersome, so we're going to develop an instantaneous description, or ID notation, for Turing machines similar to what we use for pushdown automata. But in a sense, the Turing machine IDs are even simpler because the input and tape contents are combined into one string. Moreover, we represent the state and the head position by embedding the state to the left of the symbol being scanned. We'll always assume that state symbols are chosen so they do not conflict with tape symbols, and thus we can always tell which symbol is the state. As we suggested in our little example, the Turing machine gets its input on the tape. The input, which is always a string of input symbols, is placed on the tape surrounded by an infinity of blanks to the left and to the right. The Turing machine begins in its start state with the head at the leftmost input symbol. If the input string happens to be epsilon, then the Turing machine's tape is entirely blanks and the head is scanning one of them. An ID is a string of the form alpha, q, beta. Here, alpha, beta is the contents of the tape between the leftmost and rightmost non-blank symbols. That is, the tape consists of an infinity of blanks, alpha, beta, and then another infinity of blanks. We should observe that after any finite number of moves, the Turing machine has only visited a finite number of tape squares, so there can only be a finite number of non-blanks. Thus, we always have a finite representation for the tape, even though it is infinite in extent. The state is q, and it is placed immediately to the left of the symbol the head is now scanning. Remember, we assumed state symbols are chosen, so none of them are tape symbols. Therefore, we can always identify q. As a special case, q can be at the right end of beta. If so, it means that the symbol being scanned is a blank. This can only occur if the Turing machine has just moved to the right and there are only blanks to the right. We use the turnstile notation, that is this, to represent one move, and we use the turnstile star, this, to represent any number of moves, including 0 moves. These are exactly as for PDAs. Here's an example which corresponds to the earlier Turing machine example, but now using the ID notation. We start off in the start state with the state to the left of the input. At the first move, the Turing machine moves right, here, and then right again. Now it is scanning a blank, and its action was to replace the blank by a 1 and move left. Notice that the state is now 2 symbols to the left of the end, and it's scanning what used to be the rightmost 0, that is this guy. It again moves right, and when it sees the 1, it enters state F and again moves right, changing that 1 to a 0. Now we'll discuss the turnstile relation formally. We have to discuss what happens on rightward moves separately from what happens on leftward moves. So suppose there is a right move where in state Q, scanning a Z, the Turing machine goes to state P, writes Y, and moves right. Then in any ID with QZ as a substring, which means that the Turing machine is in state Q and the Z is being scanned, we can replace QZ by YP. That has the effect of moving the head right, as well as making the state and symbol changes called for. There's a special case when Z is blank. Then it is additionally possible that from an ID with Q at the right end, that is this, which means that a blank is being scanned, for the next ID to replace the Q by YP. That is, the blank which we didn't see in alpha Q has been replaced by Y, that's here, and the state Q became P, P of course moving to the right of the Y that it just wrote. Now consider a left move, where again we are in state Q scanning Z. The new state will be P, and the symbol Y will be written over the Z. If there's any symbol X to the left of the state in the current ID, such as this, then in the next ID, the Z is replaced by Y, and the XQ is replaced by PX. That means that X is being scanned in the next ID, and of course we have gone to state P from state Q. But we also have to take care of the case where the ID has nothing to the left of the state, which means that there is an infinity of blanks to the left of the present head position. Then we reflect the move by replacing the Z by Y, that, and introducing a blank to be the symbol immediately to the right of the state. It's okay if the ID represents a blank explicitly, and this is one of several situations where we have to do so. However, it is important to note that the length of the ID can only grow by 1 at each move, so it remains finite after any finite number of moves. There are actually 2 ways to define the language of a Turing machine. Final state is one of these ways, of course. Formally, L of M for a Turing machine M is the set of strings of input symbols W, such that started in the initial ID, that's Q0 W, with W on the tape, M gets to some ID with a final state. The other way to define a language is by halting. we define h of m to be the set of input strings w such that started in the initial ID again. M gets to some I for which no move is possible. The two methods of defining languages define the same class of languages, as we can show by simple Turing machine constructions that are not too different from how we show that PDAs accepting by final state and by empty stack have the same language defining power. Given a Turing machine M, we're going to modify M into a new Turing machine M prime. The language M prime accepts by final state, M prime will accept by halting. We can easily make the final states of M be halting states by removing the rule for delta of q and x whenever q is a final state. But we have to protect against the possibility that M halts without accepting, because that M prime would then accidentally accept. So for M prime, we introduce a new state S, whose job is to make sure M prime never halts. Once M prime is in state S, on any tape symbol x, M prime stays in state S, leaves the x as it is, and moves right. Thus, M prime will always have a next move in state S. Eventually, it will get to the infinity of blanks to the right on the tape and look at them one at a time. And to make sure M prime doesn't halt accidentally, whenever delta of q and x is undefined for M, and q is not a final state, we'll have M prime enter the state S. The construction in the other direction is also pretty easy. Now we assume M accepts some language L by halting, and we want to modify it to become M double prime, which accepts L by final state. We introduce a new state F, which is the final state of M double prime. F has no move, so in fact M double prime will also halt when it accepts, but it doesn't matter. Once a Turing machine enters a final state, if acceptance is by final state, then nothing it does in the future will negate the fact that the input was accepted. If M halts in any situation, that is, delta of q and x is undefined, then define it and make the next state be F. We now have a proof that the class of languages accepted by Turing machines using final state is the same as the class of languages accepted by Turing machines using halting. The name for this class of languages is the recursively enumerable languages. You might rightly wonder where this name came from. It actually predates Alan Turing's paper describing Turing machines, and it refers to an earlier notion of anything we can compute. I'm not going to say more about that. But there's another important class of languages related to Turing machines. These are called the recursive languages. These, we shall see, are a proper subset of the recursively enumerable languages. An algorithm, formally, is a Turing machine accepting by final state that halts on any input regardless of whether that input is accepted. This notion of an algorithm is consistent with the informal notions you may have learned. However, it is limited to acceptance or rejection of input. That is, all algorithms in this sense render a yes-no decision but do not compute an output. We can extend the notion of what a Turing machine does to allow it to produce output and then halt, in which case we have exactly the same notion of algorithm that is taught in freshman computing. A language that is accepted by final state by some algorithm is called a recursive language. This term too comes from the history of attempts to answer the question, what can we compute, prior to Turing's insights. For example, every context-free language is a recursive language. You can implement the CYK algorithm for any context-free language on a Turing machine. That Turing machine will halt once it has computed the triangle of sets of variables and checked whether the start symbol of the grammar is in the final set. But the recursive languages go way beyond the context-free. In fact, it is very hard to come up with a language that is not recursive, except by using tricks like the diagonalization we discussed earlier.